So thank you very much, Nalini, for the invitation. So today we speak about joint work with Amol Agarwal and Patrick Lopato about mobility edge for Lévy matrices. So I will define those words. So I will start with the mobility edge. What is that? So I'm not. I don't think I'm doing mathematical physics, but this is a concept of mathematical physics, so maybe I am missing a big part of it, but I will tell you what I understood about mobility edge. Okay, so you consider, for example, the Anderson tight binding model. Okay, so which is from 1958. So what is that? You take you consider an operator which is you're on ZD. Okay, and the dimension is larger than 3. And you consider an operator of the following form, which is a Laplacian on ZD. So this is a discrete Laplacian. Okay, you jump with you put weights 1 to all your neighbors, and maybe you subtract you subtract 2D times the identity, and you perturb it by introducing some random disorder, where V is in the simplest model is a diagonal operator. So it's a diagonal operator. So you have considered operators of L2 of ZD. So it's a diagonal operator where the coefficients are just IID, for example, uniform on -1, 1. Okay? So you just add some impurities, some random potential on all vertices of your lattice. Here's the Euclidean lattice. And what Anderson has... So the spectrum of so you think of theta as being the strength of the disorder. Okay. So the spectrum of the Laplacian on ZD will be, let's say, 0, 4D. So this will be theta, and this will be the set of energy. So the eigenvalues of the spectrum, this is the real line, so you consider this is the spectrum of H0. Maybe we put okay, this is this interval, and when you, for a given theta, the spectrum, for a given theta, the spectrum of this operator, if you take ID uniform, is simply this interval plus theta. Okay? And the following phase diagram is conjectured for many years now. That you have some shape like that. That if you fix some energy level, here, for example, inside the spectrum of H theta, at small enough disorder, the spectrum will continue to be absolutely continuous. And for large disorder, it will become pure point. And this blue curve, theoretical physicists have no doubt that it will be a nice curve. This is called the mobility edge.
Sorry, the yellow lines are the spectrum?
Yes, so here there is no eigenvalues. And here's everywhere, here this is just pure point spectrum, and here it's absolutely continuous. Okay, sorry for the messy diagram. Maybe like that it's more clear. Okay, so proving that is hopefully difficult and has been open for many years. So, but if you replace, there have been some progress when you take simpler lattices, and the simplest one is the infinite deregular tree that we just saw in Nalini's lecture. So you consider you replace ZD by maybe I will just remove that. So proving that is open. I mean, what is it's probably one of the main open problems in mathematical physics. So if you replace, you change your lattice. Okay, you consider the same operator, still the IID diagonal. Now you have to change slightly your axis to make the same picture. So the spectrum, we just saw that the spectrum of the Laplacian, so maybe we'll take the adjacency matrix, the adjacency operator. So its spectrum will be this interval. Okay, so here I put -2 square root d minus 1. Here I put d. Okay. And so here you have 0. Okay. And except that you have to change slightly here. Okay. And it's conjecture that the phase diagram looks like that, but the same phenomenon occurs, that for the lattice, for this infinite tree, you have the same phenomenon that the absolutely continuous part is stable with respect to weak disorder when theta is small. And at some points, it breaks and the spectrum becomes pure point. And this blue curve is again the mobility edge associated to the to the Anderson model for the infinite irregular tree. So on these models, have been mathematics has been quite successful. So the physicists have understood so probably this is Toules and Abu Shakra in 1974 who have introduced this model and essentially understood how to solve it. And I will mention some work of Eisenman and Molchanov of 93, yes. And other results by Klein in 97 and Eisenman and Warzel. 2013. Okay, so what does this work say? Okay, so this is called Eisenman has introduced. So I will not mention much this paper, but this paper shows that for this model, at small energy, the spectrum continues to be absolutely continuous. Okay, this paper by Klein. So what has done Eisenman in these two papers? He introduces following what the Toules and Abu Shakra have done. He introduces if a Lyapunov exponent that you define as follows. So you take L an integer, okay. You will the usual way to study the spectrum of such operator is to introduce its resolvent, okay. So I will remove the dependency, the explicit dependency in theta to not to have too ugly notation. Okay, so you consider the resolvent when z, let's say, is in is a complex number with positive imaginary parts. Okay, and let's call O the origin of an origin of your tree, and you define phi, capital Phi L of S Z. So S is a number between 0 and 1. Z is, as I said here. This will be the expectation. So since you have some randomness, this operator is random due to the presence of the random potential. So you will take the average of the modulus of the amplitude over all vertices which are at distance L. So I will use the same notation than Nalini. Okay, so this is a set of vertices at distance L. Okay, so you sum all vertices at distance 2 here, and you sum the S power of the module of the resolvent. Okay? And under mild assumption, by some subadditivity type argument, you can prove that this converge, the growth rate of that converge as L goes to infinity to a function which is called the Lyapunov function. Okay? Now this Lyapunov function, you want to, in order to study the spectrum, you want to take Z. It has a positive imaginary part, but now you want to take a tangential limit to the real axis, okay? And you, for some reason, you also want to take S as close as possible as 1. Okay, so you define, you can define, I mean, this is a difficult part, but you manage to define, in some sense, the limit as S goes to 1 of the limit, so maybe I should put as Z converge to E of phi of SZ. Okay, so this is under some assumption you can prove, for example, in this model, if the V are IID uniform, Eisenman and Molchanov and Eisenman and Warzel tells you that you can define almost everywhere this number. It will be defined for almost all E. And now to come back to this picture, what they say is that what Eisenman and Molchanov says is that if so I'm sorry, it's a kind of technical topic, so I will put a lot of things in the carpet. But
so sorry, when you write limit in quotation mark, it means
because you have to take
almost everywhere.
So I think this limit is okay, but now sometimes you have to be sure that sometimes the lim, sometimes you take the lim sup.
Okay.
That's why that's not exactly like that, but they define it, Eisenman and Molchanov. They define two functions, one with the lim sup, one with the lim inf. But okay, for the purpose of this talk, I will just assume that I will make a rough theorem. Okay, it's so Eisenman and Molchanov, they say that if phi of E is negative, then you are then you're pure point in the sense that your operator is purely is pure point at the energy level E. Okay, it has to be true in an interval, but and Eisenman and Warzel, they prove the converse statement. So this I will essentially give you the argument for it. It's kind of very simple. And what was more difficult is to check that if the converse property is true. So again, since I hide, this is not exactly the converse because there are lim inf and lim subs which are hidden in these statements. Then your operator is absolutely continuous around energy level E. Okay, so.
And around means in a neighborhood?
Yeah, so here it's in a neighborhood. And here also. Okay, so let's check why is it related to this problem. This can be done in. There is no mystery in it. Maybe I will write it here. What you would like to understand is you take Z of the form E plus I E eta, okay? And you have this Ward type formula which tells you that the imaginary part of R is eta times R star. Okay, so if you specify it to the diagonal coefficient at the root of your tree, we'll find that this is eta times, I will just expand it, over all v of the modulus of R0 v squared. Okay, so the expectation of in power s, this will be s times.
So sorry, the second line is some shorthand notation for the
This
first
is
one?
true. That's the imaginary part of the resolvent is equal to eta times r star. It's just because the imaginary part of 1 over lambda minus z is with lambda, which is real, and z like that, it's eta divided by lambda minus. Okay, so you write things like that. Now you remember that well, VL, let's call sum of vertices of charge distance L, and I forgot an expectation. Okay, so now you remember that S is less than 1, so this is less than eta to the S, so you can put the S inside. And now you recognize the coefficient phi L of S. So here there is a Z somewhere. Okay, and now so this will be equal to sum over L of exponential, L times phi of SZ. Okay, so you see that if let's come back to Alzheimer-Molchanov, if phi of E is negative, then for some S for S close enough to 1 and E and Z, and for all Z which are close enough to E, this will be strictly less than this will be strictly negative. And then you will deduce that this is summable. Okay, and so this will be of order eta S. And so in particular, you have proved that the imaginary part of R0E plus IE eta, the limit as eta goes to 0, this is equal to 0 in probability. Okay, so this is not quite as strong as being pure point, but this goes in the good direction. Okay? And there is a converse, which is much more involved, which goes the other way around. Okay, so this Lyapunov, so this is called the fractional moment method. By Eisenman. Fractional because you take a power which is strictly less than 1. It's not an integer. And it has been pretty useful, pretty powerful, because if you want to prove this phase diagram, what you only have to do is to understand your Lyapunov exponent. Unfortunately, this is kind of difficult to compute the Lyapunov exponent, but the best use of Eisenman fractional moment method has been done by Babst. Best to my knowledge, who proves not exactly that, but he proves that as d goes to infinity, in a region which will be here, phi will be negative, and in a region which will be here, phi will be positive. and the unknown region is narrowing down as d goes to infinity. So you don't quite prove the existence of this nice mobility edge, but you prove that if you allow to be more, your tree to be more and more connecting, so the degree increases. As the degree increases, the set of energy level where you and disorders where you don't know what's happened in which part of the spectrum you are is vanishing. Okay. And there is a formula for an asymptotic as d goes to infinity. So now you have to rescale everything, and this depends on d. And there is a kind of formula for the asymptotic of phi d of e, which has been computed by Babst. Okay. And so what we did in a nutshell, so this is the mobility edge, but even for this simple model, we have not managed to prove the existence of this blue line. What we have done is we have considered another tree, which is also a random tree, but on which we can prove exactly the existence of a mobility edge. So that's what we have done with Amol Agarwal and Patrick Lopato. And this random tree, which I will not define, is tightly connected to the Lévy matrices, which I will also define. Okay? So maybe I will keep that. This I don't care. Okay, maybe we can remove Anderson. Okay, so Lévy matrices. Okay, so these matrices have been introduced by Jean-Philippe Bouchot and Patrick Ciseaux in 1940. What is that? So it's simply we take a matrix for a second. You take a symmetric matrix, let's say a symmetric matrix, and you just assume that the xij are larger than j are just id random variables, which are so independent random variables, which are in the domain and identically distributed, which are in the domain of an alpha stable law. So for this, so let's assume, just for simplicity, that the probability that xij, the law of xij is symmetric, meaning that xij and minus xij have the same distribution, and that it has a tail of order t minus alpha when t goes equivalent to t minus alpha when t goes to infinity. Okay, and alpha is some parameter between 0 and 2, which plays the role of the disorder. The larger alpha is, the less wild the random variable are, and the more homogeneous, in some sense, the matrix is. And Bouchot and Ciseaux, if you flip it, if you flip one of the pictures in their paper, you will find this. So you have to renormalize the matrices by n power 1 over alpha to obtain a matrix which is whose spectrum does not stays of order 1. Okay, so what you will see in this paper by Bouchot and Ciseaux is that you have alpha equal to 1 here. Sorry, I put alpha downwards. Okay, and you will find a curve like that. And the Bouchot and Tissot, that they say that if you fix some alpha and some energy level E, the corresponding eigenvectors here will be localized. And here you will have delocalized eigenvectors in a sense which I will not be very precise about. Okay? So this model of random matrices has been studied a lot. The first math paper about it is by Benarous and Guillonnet in 2007, 8. With Jalil, who is in the room, Shafai, we've also studied, Caputo, and Pietro Caputo, we have also studied this paper, this model in 2011, and we have also done some work with Alice Guillonnet on this paper. So we're trying to prove, towards the goal of trying to prove this curve, and there have been some very nice results by Agarwal, Lopato, and Yao, and also one with Marcinek in 21. And in these two papers, they essentially settled, they prove that everywhere here the eigenvectors will be delocalized. In this paper, to try to connect with this one should be more in red. In this paper with Jalil and Pietro Caputo, what we have done is we have proved that in some sense these matrices they have a scaling limit when n goes to infinity, and that this scaling limit is looks very much like the Anderson model on the regular tree, except that the tree is infinite and it's not, and the randomness does not come from an IID potential of the diagonal, but from randomness given by Poisson weights on the edges of the tree. I will define this tree for you. So it's a tree which has been introduced in a completely different context by David Aldous in 92, and it's called the Poisson weighted infinite tree, aka the PUIT. So how do you define it? So you have to, it's an infinite tree, but it has also an infinite number of neighbors. Every vertex has an infinite number of neighbors. So its vertex set, you can use Neveu's notation and define its vertex set to be the set of finite integer sequences. Okay? And so the root is the empty sequence, which I will denote by O. Its neighbors are all sequence of length 1, so are just regular integers. Then the neighbors of, for example, 3 are integer sequence of length 2, which starts with a 3, and so on. Okay, I stop here because. Okay, so these are the vertices and the edges of my infinite tree. Now I have to put these Poisson weights. So to an element V, which is in this vertex set, okay, I associate a family of, to each vertex of my tree, I associate an independent Poisson point process. on R without 0 of intensity measure alpha over 2 absolute value alpha over 2, and this is the Lebesgue measure. Okay? So you have a set of, so for each V, psi V, I will say it in other words. Psi V, you can see that as a collection of points. Psi V1, psi Vk, k an integer. I will order them so that they have the absolute value of psi V1 is larger than the absolute value of psi V2, and so on. You see that the intensity measure, it explodes at 0. So this Poisson point process, they have an accumulation point at 0. And these weights, for example, the law of this largest weight, you can compute it, for example, just to what is the probability that this is less than t. This is the probability that my point process has no point on minus infinity t, minus t plus infinity is 0, anti-set. But the number of points it has is 0. Okay, so this is twice the probability that the Poisson measure at is 0. It will be the exponential of minus twice times t to infinity of alpha over 2 x power minus alpha. Okay, did I make t correct? Seems like it. Okay, where was it, the 2? Okay, so it's exponential of, and so this is exponential minus t minus alpha. So I think it's a Fréchet distribution. That's true. Okay, so you can compute the law of its maximum, and you can make a lot of computation of this process, of course. And so I come back to my point process. So it has an extremal point, psi v1. And so what I will do, I will put a weight, if here it's v, it has its neighbors. I will put weight psi v1 to between v and v1, psi v2 between v and v2, and so on. Okay, and now you can define an operator t by for compactly supported function on v by saying that t v w will be equal to psi v vk, and this will be equal to t wv if w is a case of spring of v and 0 otherwise. Okay, so it's not exactly correctly written, but you understood. Okay, so I define an operator, so it's a random operator, and the weight I put between a vertex to its offsprings is given by these Poisson weights. Okay, so now I claim that this operator, which looks complicated, but that this operator is a scaling limit of these matrices. Okay, so this is not very difficult to check. Maybe it's a simple computation, but if you look at the orders that you have a vector here, for example, if you look at the first column and you reorder it, okay, so you reorder it by a sequence of points, psi Okay, so you do a monotone reordering of the first column of your matrix. Okay, if you look at it's a standard probability exercise to check that this vector, okay, will converge as n goes to infinity to the points of my point process under this assumption. Okay, so this set will converge to the set given by my point psi vk for a fixed v. Okay, and then what is hidden in this scaling limit, that is once you have explored the first row, you will explore you will reorder the next one, and you will expanding that, you will get an infinite tree in the limit. Okay, so maybe I will not be more precise on that. And now, this operator, so we have studied it with Chalil and Petro, and it's a random operator, it's unbounded, so it's so T is symmetric, is unbounded. It's unbounded because we have seen that these weights, they have an infinite, their support is infinite. And so, but nevertheless, it is almost surely essentially self-adjoint. And okay, so what we have, I forgot to mention something. So this was Bouchot and Ciseaux in 94, and there is also another paper by Tarquini, Biroli, and Tarzia a few years ago, which have looked again at the paper of Bouchot and Ciseaux, and this was the origin of our motivation. So what they have done is they have considered again the computation that Bouchot and Ciseaux did. They did it in a smarter way, and they have proved that this curve that is conjectured by Bouchot and Ciseaux is some explicit function, is explicit, and this curve is some level set of a function of two parameters, e and alpha, and it corresponds to lambda e alpha equal to 1. I will give you an explicit formula for lambda e alpha. Okay, they did not prove that this curve exists, but they just prove that if there is a mobility edge, it will occur at level sets where this function will be equal to 1. Okay, so what we have done with my co-author, Amol Agarwal and Patrick Lopato, we have proved that their computation was correct, and that in this, for this random operator, you can prove the existence of this mobility edge, but this is, in all this region you are lambda, which is negative, in all this region lambda e alpha is positive, and you can come back by using some abstract scaling arguments. You can come back to deduce some weak form or localization or delocalization of the corresponding eigenvectors on these Lévy matrices. Okay.
Can you recall what was the red region?
That was a region where it was already known that when alpha is below 1, there is no mobility edge. The operator is always absolutely continuous, and the corresponding eigenvectors are delocalized. The only set of parameters for which it was expected that there is some mobility edge is this region when alpha is between 0 and 1. And so to our knowledge, we were happy because this is the first kind of, even if this tree looks very ugly, I mean, it looks very complicated compared to the Anderson model. It's simpler. There are some miracles occurring with this Poisson point processes. We can make computation which are not working that well for the usual Anderson model on a tree, and we can compute exactly this mobility edge. Okay. So what we prove is that we introduce the same. We use the same Lyapunov exponent, and we prove that. I will give you a theorem after that, but we prove that we have been able to compute, to make this program of Eisenman, Warzel, and Bolchanov work, and we have been able to compute the Lyapunov exponents. We prove that phi of Z is phi of E, sorry, is a log of a function lambda of E alpha, which I will give you a formula for it in a second. Okay?
And maybe on your picture, you wanted to write alpha strictly greater than 1 and instead of 0?
Lambda. Yes, thank you. Yes, sorry, I messed up with the Lyapunov exponent. And that was the other way around. Less than 1, larger than 1. Okay. Okay, so what did we prove? So now I can write a theorem. I'll try to. Should I keep that? Okay. Okay, so what is this lambda of E alpha? Okay, is a solution. It's a positive solution. It's the negative solution of lambda's quadratic equation minus 2. I will tell you what are those numbers. Real part of E lambda. It's just order 2 T alpha squared minus 1 Okay, so they solve a polynomial equation of degree 2, where T alpha is just a sine of P alpha over 2, K alpha is alpha over 2 gamma of 1 over 2, and L of E, wait a second, I will tell you at the end, and I forgot, what did I write? Okay, sorry, I could have written this differently. Okay, I will tell you what.
It's a bit difficult to
what?
to read what. It's a bit difficult to read what is T alpha and what is P alpha.
T alpha is sine of P alpha over 2, so my writing is bad. K alpha is alpha over 2, gamma of 1 minus alpha. Gamma is the usual gamma function. And this is a quadratic equation. And I didn't tell you what is L of E, but this is essentially the limit of the alpha's power of the resolvent of my operator T. So now I take the resolvent, R is the resolvent of my operator T, which is here. And you take the tangential limit, and you choose the correct branch of the fractional moment, and this is what is L of E. And there is a kind of there is an semi-explicit, there is an explicit formula for L of E.
So it should be L of E alpha.
Yes. Okay. So we proved two theorems. The first one is that, so as I said, our goal is to prove that the Lyapunov exponent defined exactly in this way. Okay, for the same, the Lyapunov exponent will be equal to the log of this number lambda, and it's called lambda because it will be an eigenvalue of some transfer operator. if I manage to arrive here. So we prove that for all E in R, if lambda of E alpha is larger than 1, so which corresponds to the localized, delocalized phase, then what we prove is that then the limit as eta goes to 0 of the imaginary part of R plus E eta, so we look at the diagonal. This goes to, this is lower bounded in probability. Okay, meaning that for, if you take for any epsilon with probability 1 minus epsilon, it will be larger than the number, positive number which depends on epsilon. Okay? So this proves a weak form of that. Okay? And in the localized phase, we prove that if you define E log of alpha, because if you see this quadratic equation, I didn't tell you what is L of E alpha, but it's not completely clear that to study the level set of this function is not easy. So a priori, you don't know if there is a unique solution, if for each alpha there is a unique solution of lambda E alpha is equal to 1. Okay, so you take the largest one. Okay, what we prove is that for all E which are larger than this number, you have the converse of that, meaning that the imaginary part of the resolvent goes to 0.
Also, so sorry, you say that you don't know if for given alpha there is a unique.
We will prove it, but in a second term.
For the, okay.
Yeah, I mean, not completely, but okay. So then, what remains? So we say that for. So now we have to study these level sets if we want to prove the existence of this mobility edge, because there could still be many possible values for each for given alpha. There could be many E's such that lambda of E alpha is equal to 1, and then our statement would be not so useful. And what we have managed to do is to essentially compute the asymptotic of lambda E alpha when alpha is close to the border, 0 and 1, and check that there is a unique solution. And this is the second last theorem. Okay, such that so here is the small c, such that for all alpha which are either small or close to 1, the set of E such that lambda of E alpha is 1. This is a single, contains a single point. And this point, which is so then this which coincides with this one, scales like 1 minus alpha up to some constant I'm hiding as alpha goes to 1, and it scales like 1 over log 1 over alpha power minus alpha over 2. 2 over alpha as alpha goes to 0. Okay, so we did not completely prove what Tarquini, Biroli, and Tarzia conjecture. So we proved that their formula was they have a unique solution in some for alpha close to 0 and alpha close to 1. And in the middle, the analysis of it's just a question of analyzing a fixed point equation, but it's too ugly to be solved, at least to us.
But numerically, it's clear that there is a single.
There is no doubt. But I mean, even Bouchot and Ciseaux had no doubt, and even Toules, Abu Shakra on the Anderson model.
But did they have this formula already?
No, Bouchot and Ciseaux, I think they made the computation they have a formula, but it's much more complicated than this one. And the formula of Tarquini, Biroli, and Tarzier is better.
So this formula was already in.
Yes, it's exactly the formula of Biroli, Tarquini, and Tarzier.
Okay.
Okay. I have to spend a lot of time explaining so I can just tell you okay, I will not. What can I tell you in 10 minutes? I can tell you what do we prove, or what is the strategy of the proof, and then just give you one property of alpha stable laws which could make you hint that this model is in fact simpler than the model on the usual model of the Anderson model on the infinite tree, on the infinite regular tree. So our proof is our strategy for theorem 1. I mentioned also, we know that this condition is that lambda of E alpha is always larger than 1 for E small. So we know that this, and we also know that this supre is finite. Okay, so what is the strategy? The first point is to prove this. So we prove that if we introduce the Lyapunov exponent exactly like that, we prove its existence. So using the regularity property, since you have all the random variables have some densities, we have managed to prove that this number phi of E exists. And we prove that if phi of E is positive, maybe to save me some time, I will call, if you want, this property, I will just call that delocalization, if you agree with that. And I will call that this property localization at E. Okay? So we prove that if, for any E, if the Lyapunov exponent, which I don't know how to compute, is positive, then deloc at E. Okay? So this proof is a refinement of the Eisenman and Warzel paper in 2013, and I have no time to explain you the strategy, but it follows roughly the same idea. Now we have the same statement for the Eisenman-Molchanov, that if phi of E is negative, then you have localization at E. So this I already gave you I've already given you the proof at the beginning. Okay. Then we prove that if you don't know to compute this number, but we prove that if phi of E is negative, then phi of E must be equal to lambda of E alpha, to log of lambda. This is probably the most interesting yes. Oh no, sorry. we prove that if this is true, if log is true, then the Lyapunov exponent must be equal to the log of lambda of the alpha. And the last property we need is a continuity property that phi of SE is convex in S. So it's defined for S in alpha 1. And it's continuous. It's continuous, it's convex and non-increasing. Non-decreasing. And this function is continuous. What is difficult is the continuity in E. It's continuous in E on the when phi at the point where the phi is negative. Okay, so if you have a point where phi of SE is negative, you know that this will be locally continuous. And from these 4 points, you can deduce the theorem. So this is a kind of continuity argument. For example, let's check that. So you first prove that, you know that for E large, this conclusion holds by some technical argument I will skip. You know it's a continuity argument. So you know that for E large, this is true. Then since this is true, you are localized, you know that phi of E will be equal to the log of lambda of E. Okay, so, and this is, and now since phi of E will be negative, and this is continuous when phi of E is negative, you can take a point which is slightly less than what you had before, and where phi of E will be negative. Then it will be localized. And since it will be localized, the new value at the new point E, you will have again this identity. And you will be able to, by a continuity argument, to go up to the largest point where you meet this boundary. Okay. That's why we really had to, it's a continuity argument, and we really have to start somewhere, and we start at infinity. Okay. And in one, so it's a pretty long paper. So I will just, so when there are many properties of alpha stable laws, and this point process. So the easier to state one is this identity. But in fact, the fact that you are able to make computation rather explicit in this model, I didn't define you L of E, but is due to when you take sums of, if you look at the resolvent, you have a recursion equation for the resolvent, which is standard on trees. And you will find, if you remember my notation, you have this recursion on the resolvent, where these are the weights of my Poisson process at the first. And this is the resolvent of the diagonal operator at K, where in the tree where you have removed, if this is K, you remove this edge. So you disconnect K to the rest of the tree. And this one, by the recursive properties of the tree, this one and this one have the same distribution. Okay, but now you have a property that this point process in K, it's a Poisson point process on R plus of intensity measure alpha over 2 x minus alpha over 2 minus 1 dx, okay? And it is the subordinator of an alpha stable process. So in particular, if you take psi k, which are ID non-negative variables, if you take sum of psi k, I will use the same notation, squared, this has the same distribution as this variable times simply the expectation of x1 power alpha over 2 power 2 over alpha. So the way this sum depends on the law of xk is very low dimensional. There is an order parameter which is just the alpha over 2's moment. And this makes all the magic works. Okay, I have no time more, but thank you for your attention.